Well, welcome to Unit 4. Today we make the turn. It's a sharp turn, it's a nasty turn, it's a big turn. Today we make the shift to areas. We're going to estimate areas using, well, rectangles. Consider the following. Let's imagine that this is some velocity function. Velocity in miles per hour, time here measured in hours, and I'm driving, and my velocity is 75 miles per hour all the time. All the time. Just driving 75 miles an hour all the time. And I want to know how far I traveled between time equals 7 and time equals 9. You and I would both agree that if I drive for 2 hours, this is 2 hours, at 75 miles per hour, that's 150 miles. Well, where is that 150 miles in the picture? That 150 miles is the area of this rectangle, whose height is 75 and whose width is 2. The distance traveled is 75 miles per hour times 2 hours. That's 150 miles. And the units even work out. If you multiply miles per hour by hours, you get miles. So this is a beautiful thing, because now I know that if I want to get distance from a velocity graph, I just take the area under the velocity graph, but over the x-axis from starting place to stopping place. But what if the velocity varies? What if the velocity is not the same all the time? Well, then we have to approximate. I want to estimate the area under f of x equals x times sine x from x equals 0 to x equals 3. And it'll help if we get a picture. So let's bring in a picture. Let's bring in a picture of x times sine x on 0 to 3. Maybe we'll go 0 to, 0 to 3. Let's see how that looks. That looks pretty good. So we'll take a picture because it lasts longer. There we go. This is the area I'd like to estimate. And I'll lock that in place for us. So there are many ways for us to estimate this area under the curve. One of the ways is to do what's called a left rectangle approximation method. And so in a left rectangle approximation method, we take the left endpoint of each interval, and that left endpoint of each of my, I'll use 3 subintervals, you could use 6 subintervals or 12 subintervals. The left endpoint will tell us the height of the rectangle we're going to use to approximate the area under the curve. Because see, friends, I don't know how to find the area of a curvy thing, but I know how to find the area of a straight thing. I know how to find the area of a rectangle. So I'm going to use the left endpoint of each subinterval, and I'm going to say that's the height. Those rectangles roughly approximate the curve. And so if I'm looking to do a left rectangle approximation method, the left endpoint is 0, the left endpoint is 1, the left endpoint is 2. And so the areas, since the widths of all the rectangles are 1, the heights of the rectangles are the areas of the rectangles. And so I go to my calculator and I ask it for 0 times sine 0 plus 1 times sine 1 plus 2 times sine 2, and I get 2.66. 2.660. Well, of course, we could do a right rectangle approximation method. In the right rectangle approximation method, we use the right endpoint of each interval. Really? We use the right endpoint of each interval to give us the height of the rectangle we're going to use. And so we say from 0 to 1, we're going to use the height at 1. And from 1 to 2, we're going to use the height at 2. And from 2 to 3, we're going to use the height at 3. And so we get 1 times sine 1 plus 2 times sine 2 plus 3 times sine 3. And we go ask our calculator what that looks like. And our calculator tells us 3.083. Now, of course, some people want to use a midpoint rectangle approximation method. A midpoint rectangle approximation method. And in a midpoint rectangle approximation method, we say, okay, between 0 and 1, I want to use the height at 1/2. I'm going to let that drive the rectangle height. Between 1 and 2, I'm going to use 1.5. And between 2 and 3, I'm going to use the height at 2.5, because that kind of splits the difference. That's a little bit tougher to sub in. We're going to ask for 0.5 sine of 0.5 plus 1.5 sine of 1.5 plus 2.5 sine of 2.5, and that's going to be approximately, eventually 3.232. Now, none of those is the actual area under the curve. None of them. Some of them are closer than others, but none of them is the actual area. We're looking at an approximation. An approximation. So what if I wanted a better approximation? Well, if I wanted a better approximation, I would find more rectangles. I would do more rectangles. So maybe I do 6 rectangles instead of 3. Maybe I do 6 rectangles instead of 3. And maybe I do the right endpoint on those 6 rectangles. Maybe. And I add up all 6 of those rectangles. And if I do that, then I've got 6 rectangles, each of whose widths is 0.5. So I've got 0.5 times all the heights, and all the heights are 0.5 times sine of 0.5 plus 1 times sine of 1 plus 1.5 times sine of 1.5 plus 2 times sine of 2 plus 2.5 times sine of 2.5 plus 3 times sine of 3, and I get 3.158, and that's better. I mean, it's a right rectangle approximation with 6 sub-intervals, and I get 3.158. That's better, but if I wanted to be better than that, I would need more rectangles. So maybe I go with 12 subintervals, or maybe I go with 24 subintervals, or maybe I just keep going with smaller and smaller subintervals until I have infinitely many, infinitely thin subintervals. what happens then? Well, then we have what's called the definite integral. The definite integral. And this is where your calculus is going to come in very, very big. Let f be a function defined on a closed interval, AB, for any partition capital P of AB. And by the way, the partition is just the way we break AB into subintervals. When I broke AB into 0 to 1, 1 to 2, 2 to 3, that was a partition of AB. Let C sub k be chosen arbitrarily in each subinterval. In other words, we're going to pick C sub k in every subinterval. We're going to do it arbitrarily. Maybe we pick the left endpoint. Maybe we pick the right endpoint. Maybe we pick the midpoint. Maybe we pick a random point in between. If there exists a number I such that the limit as the norm of P approaches 0 of the sum k goes from 1 to n of f of C sub k delta x sub k is equal to I, no matter how P and C sub k are chosen, then f is integrable, that's a big word, and I is the definite integral of f over AB. What the heck did he just write? Well, the norm is the largest subinterval. Because you can choose the subintervals don't have to be all the same size. You can choose subintervals of various sizes, depending on what you need for a particular situation. So in theory, you could have subintervals of various sizes. And if you do, then we have to eventually let the largest subinterval get smaller and smaller and smaller and smaller and smaller. In other words, when we say the norm is going to 0, we mean that the number of rectangles is getting larger and larger and larger and larger and larger. Now, what is this? This is the area of the kth rectangle. Its width is a delta x, and its height is a function value. Its width is a delta x, its height is a function value. So what we're doing is we're adding up a whole slew of rectangles, and the largest one is getting thinner and thinner and thinner and thinner and thinner. If we get thinner and thinner rectangles and add up more and more of their areas, and those sums get closer and closer to some number I, then that I is the definite integral. By the way, side note, if all the subintervals are the same width, then you've got the limit as n approaches infinity of a sum of infinitely many areas, each of which is the area of a rectangle. If that limit, if this limit goes somewhere, if I take more and more rectangles, they're thinner and thinner and thinner, and that sum goes somewhere, then that is the definite integral from a to b of f of x dx. And that is the familiar notation to you. By the way, the theory goes, all continuous functions are integrable. All of them. All continuous functions are integrable. So what do you know? You know that the definite integral, see, this is the stuff that's going to come flooding back like mad. You know that the definite integral is the area under a curve. You know if y equals f of x is non-negative and integrable. Incidentally, all continuous functions are integrable over AB. Then the area under f of x from a to b is the definite integral from a to b of f of x dx. Now, of course, it makes sense that there's a dx here because in the original formula, there's a delta x, and that represents a teeny tiny change in x, just like dx represents a teeny tiny change in x. And so this is the stuff that you're familiar with. If you're supposed to find the integral from -3 to 3 of 9 minus x squared dx, then how do we do that? Well, radical 9 minus x squared is this thing. It's a semicircle. I'm looking for that area. I don't have to do any real calculus. I just have to make the connection between this integral and this region and say, ooh, that's half of pi r squared. Done. And by the way, they love that. They love when you can do that. Oh, I should probably do one more thing. Let's do one more thing. What happens if the function is negative? We'll go red for negative. Then we're talking about what we call, I'm using air quotes now, negative area. You can't have negative area. I know that. What I mean is area below the x-axis. And if we take area that is below the x-axis, then we get the same answer, but negative. So we refer to positive area and negative area as areas above the x-axis and below the x-axis, respectively. So if I have some function from a to b, and it does this, and I want the integral from a to b of f of x dx, this is f of x. What is that? That's the area above the x-axis minus the area below the x-axis. And this is the stuff that comes flooding back to you, I hope. Awesome. So tomorrow, I get to hit you with, some basics on how to evaluate that stuff without a calculator. Ooh, some of that stuff. And then we're going to set up the fundamental theorem of calculus. We're going to talk about average value of a function, but that's coming up tomorrow and not today.